So in the last lecture, we discussed the IV characteristics of a ballistic MOSFET. And we have been focusing on the virtual source as we've been developing our understanding of MOSFETs. What I'd like to do in this lecture is to look at the velocity of electrons at the virtual source. So we have been focusing on the top of the energy barrier between the source and the channel, the location that we refer to as the virtual source. And we know that current is charge times velocity. We'd like to examine the velocity now. We've been focusing on this point because we know the charge at that point. But now we have a couple of questions about the velocity. We want to understand what is that average velocity at the top of the barrier? How does it depend on drain voltage? How does it depend on gate voltage? Okay, so the approach we're going to use is very straightforward. We know that the definition of current involves a charge and a velocity. And we have an IV expression that gives us the current through a ballistic MOSFET at any drain to source voltage. So we're simply going to put these two together, equate them to each other, and solve for the velocity. All right, so let's take a look at that. We're going to focus on, first of all, on how does that velocity change as we increase the drain to source voltage. Well, the result is very simple. We have an expression by equating those two expressions for the drain current. We get a very simple expression for the average velocity at the virtual source as a function of drain to source voltage, and we'll simply examine that expression and plot it as VDS is increased. So as we increase the drain to source voltage from a small value to a large value, the average velocity at the virtual source will increase at first linearly, and then it will saturate. So for small VDS, the average velocity is proportional to VDS. For large VDS, it becomes independent of VDS, and it saturates at the unidirectional thermal velocity. That's what this equation says. You just plot it, and that's what we get. Let's look a little more carefully then at the low drain to source voltage limit. Here's our general expression. We can expand that assuming that the drain to source voltage is small compared to KT. Then we can remember that e to a small number is 1 plus the small number. We can expand the exponentials in this expression. And if we do that, you'll see that something remarkably simple happens. For small drain to source voltage, as expected, the velocity is proportional to the drain to source voltage, and the constants of proportionality are unidirectional thermal velocity divided by 2 kT over Q. Well, let me multiply by length in these constants out front, and let me then divide by length, so I've done nothing. Now, I can recognize drain voltage divided by length is the electric field in the channel. And I should be able to recognize this quantity too. You should be able to see that this is our friend, the ballistic mobility. So what we determine then is that out front we have the ballistic mobility, and we simply conclude that the average velocity at the top of the barrier in the small drain source voltage limit is just ballistic mobility times the electric field. A very reasonable result. We might have been able to guess that. So velocity is proportional to the electric field in the linear regime, but we have to use the ballistic mobility in the ballistic limit. Okay, now let's turn to the large voltage limit between the drain and the source. In this case, it's even easier. You can see that once the drain voltage gets above KT over Q, these exponentials are going to become very small, and the velocity just saturates at the unidirectional thermal velocity. So that's easy to see, and in between we just smoothly go from one limit to the other limit. Okay, now we'd like to understand the physics of this saturation in a little more detail. But one thing I'll point out is that when you see an IV characteristic like this, a MOSFET engineer would look at these IV characteristics and would say, aha, this is a velocity saturated MOSFET, because the drain current in the saturation region is increasing as Vg minus Vt to the first power. So this is the signature of velocity saturation. Traditionally, this is due to strong scattering in the high field region near the drain. But we've seen that the velocity saturates in a ballistic MOSFET. So the IV characteristics of a ballistic MOSFET would also look like this. So that's kind of interesting to see, and we'll discuss the physics of that saturation now in a minute. But we can point out that in a long channel MOSFET, it's scattering that saturates the velocity, and it happens near the drain. In a ballistic MOSFET, there is no scattering, and the velocity saturates at the top of the energy barrier between the source and the channel. The electric field is zero at the top of that barrier. So it saturates at the source, not the drain. It saturates where the electric field is zero, not high. That's really interesting to understand how that happens. And we will look a little more closely and get a little deeper understanding of the physics of that velocity saturation process. So the way I'd like to do that is to look at the carrier distributions in velocity space at the top of the barrier. So remember, the states are populated according to the equilibrium Fermi function. We can approximate the equilibrium Fermi function by a Maxwell-Boltzmann distribution if we're non-degenerate. We can write this F0, this Fermi function, in terms of velocity rather than energy. If we have a parabolic band, E is equal to bottom of the conduction band plus 1/2 mv squared kinetic energy. And we conclude that the distribution of velocities should be a Maxwellian distribution of velocities in the 2D plane of the channel. So this is what it would look like in equilibrium. We'd simply have a symmetrical Maxwellian distribution of velocities. No average velocity in any direction, because there is no average velocity in equilibrium. This randomness is maintained by strong scattering. The electrons and phonons and defects and everything introduce strong scattering that randomizes all of the directions. The electrons come in equilibrium with the phonons, and what we're left with is this thermal equilibrium Maxwellian distribution of velocities. Okay. So it's all about scattering in the bulk, but we're going to look at a nano MOSFET, at a ballistic MOSFET, in which there is no scattering in the channel. We're going to look at the top of the barrier and ask, what is the distribution of velocities at the top of the barrier as we increase the drain to source voltage from 0 to some large value? These are the results of this numerical simulation. So if I look first, when the drain to source voltage is 0, I have no current. I'm in thermodynamic equilibrium. I get a thermal equilibrium symmetrical distribution of velocities in all directions. No net average velocity in any direction. Now you might ask, what maintains that thermal equilibrium distribution? It was scattering in the bulk. There is no scattering inside the transistor at the top of the barrier. That's right. All of the scattering occurs in the source and the drain contacts, but we have injected the positive half of this thermal equilibrium distribution from the thermal equilibrium source, and we have injected the negative half of that distribution at the top of the virtual source from the thermal equilibrium drain. Put those two together, we get an overall thermal equilibrium symmetrical distribution. Now, increase the drain to source voltage a little bit. That lowers the Fermi level in the drain. That means it's less likely that the states at the top of the barrier can be occupied because the Fermi function for the negative velocity states has been lowered. You'll see that the positive velocity distribution is the same. The negative velocity distribution is smaller because the Fermi level has been lowered in the drain. That's where the negative velocity electrons came from. The overall average velocity now would have a positive component in the x direction, because I have more electrons with positive velocities than I do with negative velocities. Increase the drain voltage a little more, and the contribution of the negative velocity electrons becomes even smaller. Increase the drain to source voltage enough, and there are no negative velocity electrons. I only have positive velocity electrons. If I continue to increase, I'll get the maximum average velocity in the x direction because I'm only averaging over x directed electrons, not minus x directed electrons. But if I increase the drain voltage even more, nothing will happen because I have no more negative electrons to suppress. So this is the physics of velocity saturation at the virtual source. It occurs because we depopulate the negative half and basically don't do anything to the positive half. Now, those of you that are looking carefully might notice that the positive half of this thermal equilibrium distribution is a little bigger than the positive half of the initial thermal equilibrium distribution. You know, what's that all about? Well, what that's all about is that MOS electrostatics demands a certain charge at the top of the barrier, minus C inversion times Vg minus Vt. That always has to be the case. If I have only positive velocity electrons, the MOSFET has to react by pulling the barrier down a little bit, letting more positive velocity electrons in, such that the total charge is what the gate demands it to be. So there's some really interesting physics you can see by looking at these results closely. So under high drain to source bias then, we have only positive velocity electrons. The average x-directed velocity of these that have an x component in the plus x direction, but are scattered in various angles in the xy plane, the average x-directed velocity of that distribution of velocities is what we call the unidirectional thermal velocity, or we'll also call it the ballistic injection velocity. This is the velocity at which carriers are injected into the channel in. Now, we can do the calculation more generally with Fermi-Dirac statistics, and you'll see that it involves some Fermi-Dirac integrals, which depend on the location of the Fermi function with respect to the bottom of the conduction band. And that can become important, especially when we go above threshold. Okay. The unidirectional thermal velocity is the non-degenerate limit of this more general ballistic injection velocity. If we do that calculation for silicon, the results will look something like this. In the non-degenerate limit, we get the unidirectional thermal velocity. That would basically be sub-threshold. Once we go above threshold, the velocity starts to increase as the influence of this Fermi-Dirac statistics. 10 to the 13th carriers per square centimeter is about the largest density of electrons. That's what you might get under on-current conditions in a MOSFET. And you can see that under those conditions, the ballistic injection velocity could be significantly larger than its non-degenerate limit, square root of 2 kT over pi m. So in analyzing real devices, this is something that you're going to want to be aware of and familiar with. It complicates the analysis a little bit because we have to deal with Fermi-Dirac integrals, but it's really important to do that if you want to be careful about the numbers. Now, if you're interested in more discussion about how we do these calculations under more general conditions with Fermi-Dirac integrals, here's a reference for you to consult. So let's wrap up. We've seen that in a ballistic MOSFET, and this was a surprise when people first started thinking about ballistic MOSFETs, the velocity still saturates. But it saturates for a completely different physical reason and at a completely different location. It saturates at the top of the energy barrier between the source and the channel, at the virtual source where the electric field is 0. And it saturates at a value we call the ballistic injection velocity. And that ballistic injection velocity is a key figure of merit for nanoscale transistors. You'd like it to be as high as possible to get the maximum current that you can get. All right, what's next? So we've seen how to treat the diffusive case. We saw that long ago. We used the traditional expression with the diffusive mobility. We've seen how to treat the ballistic case. We used the ballistic mobility in the low drain bias regime. We used the ballistic injection velocity in the high field regime instead of the high field saturation velocity. But we really need to know how to treat MOSFETs between these two limits because that's where most transistors live. That's the subject of our discussion in the next lecture.